Hopefully we can get the picture too.
Just working. It was. Okay.
Well.
Let me just mention while we're getting things set up that speakers should send their slides to hipack1@gmail.com. HIPACC1@gmail.com. If you haven't already given them to the tan line in the back row, using a memory stick. So memory stick's fine. See tan line is on the far left side, the back row, or email. And the talks are all being video recorded, and that's why you have to use a microphone, because otherwise the video doesn't pick up the audio.
Very good. Okay, so good morning. I apologize for this wonderful bar down here. We don't know what it is due to. It must be a European feature. So I've regularly used in the past this occasion here to show some of our new work, and we'll do that again. Linda Tacconi on Thursday and I here. And so today I decided to pick 3 topics of our new work with mostly CHEMOS, as you will see in a second what that is. And that is a study of the angular momenta, Baryon fractions, already pushing out into the halo, and then also the outflow story, which is further emerging. Now this is work which involves a large number of people, in particular Natascha Förster-Schreiber, Andy Burkhardt, who is sitting in the back, Linda Tacconi, also sitting in the back, Emily Wisniewski and Stein Witz, and a whole set of characters from mainly the CHEMOS 3D team in Munich. Okay. So the work we've been doing over the years is concentrated mainly on integral field spectroscopy in the near-infrared on the VLT, and until recently we've been using the Symphony spectrograph, which is a single IFU unit, and you can couple it with adaptive optics and laser stars, so that you get about 1 to 2 kiloparsec resolution. And so that's been a very successful project. Over a decade, we were able to assemble about 110 objects, which of course is a very small number. So the big progress which is happening right now, both on the Keck with MOSFire and, as you will see, on the VLT with CHEMOS, is to now go into an era where we can do many more objects by multiplexing. Now, with CHEMOS, we have a situation where, due to the work of the instrument team, led by Ray Sharpless in Durham, there's 24 IFUs. So one goes from 1 IFU to 24 any given time. IFU pixel scale is 0.2 arc second, and you get about 2.5, 3 arc second fields of view. So with that, we've, as the GTO team, we've been able to carry out a major survey called CHEMOS 3D, coupling the 3D HST base sample with the CHEMOS survey. And the goal is to go to about 600 objects, stellar mass selected in the redshifts range 0.7 to 2.7. And of course, that's in the southern 3D HST candles fields. So we have excellent auxiliary information, imagery from the HST. That's very important, of course, for this work. Now, the one disadvantage of CHEMOS is it's seeing limited. So we only get sort of the broader pictures, but it's remarkably successful. Perhaps in contrast to what many other people are doing in the field right now, we are concentrating on getting very high quality information per object. So we're not trying to get more than 1,000 objects. Instead, we are going for deep integrations. The main reason is we want to expand the parameter space sampled from the main sequence, as you will see, down to below the main sequence where the quenched objects are. and also get good enough information in terms of profiles and also kinematics on individual galaxies. That's very important to us. So we're integrating up to about 20 hours per object. So that gives us very high quality information. So here you see the main sequence in this redshift range. There's the 3D HST parent sample below as a function of stellar mass and star formation rate. Then with Symphony, my thing gave out, so I have to see whether I can. With Symphony, you can see that's what we assembled in a decade, where the red objects and the yellow objects here are covering the main sequence, but not below the main sequence. And because we were using classical UV selected or optically selected galaxies, this covers mainly the blue part of the population, does not get into the reddish, dusty part of the population, and certainly not into the quiescent population. So with KMOS 3D, which is now running for 2 years, another 2 to go, we are more than halfway there. And that's what we've assembled already. So that's where we are, about 450 galaxies. And you see the blue objects are the detections, the black objects are the targets, which we have in our sample. So we actually have quite a number of detections below the main sequence. And as I said, covering the stellar mass to star formation rate main sequence from about 10 to the 10 solar masses upwards. We have placed quite a bit of emphasis over the last 2 years on the high mass side, because there it is that we are expecting to see a number of the phenomena on quenching, which we would like to study. And you will see one aspect is indeed the issue of the outflows driven by central active galactic nuclei. So here are, in picture form, the stellar mass star formation rate plane at redshift about 1, so that's one of the slices we have. And you can see here the HST imagery in 3 bands posted on the main sequence plane. And you can see that the galaxies here at redshift 1 are still looking reasonably symmetric and normal, although you're beginning to see some of the asymmetries and clumpiness and so forth, which is typical at the higher redshift. Now you know that the main sequence is also a structural sequence. So here from the work of Stein-Voits, you can see that at all redshifts between the local universe and redshift 2.5, if you plot on the main sequence, which is the white line here, in color, the Sursich indices, you can see that at all redshifts, the main sequence coincides with n about 1. So there would be exponential profiles which you would identify with structural disks. Now redshift 2, here's the images of the redshift 2 sample we've observed, is already quite a bit more ratty looking or clumpy looking, very, very different from the local universe. But now, this clumpy asymmetric morphology, which has been noted for 2 decades, changes if you now look at both the stellar surface density distribution instead of the imagery, and also the kinematics. And the technique which in our group Stein-Voits has pioneered, but it's been used elsewhere, of course, as well, is to basically take the multi-band Candle's imagery and then extract from that, on the right side, the stellar surface density distribution. So you get from a fairly clumpy appearance on the ultraviolet, rest frame ultraviolet side, to a much more regular looking system, which in this case obviously has a central concentration, which you might call a bulge. And so indeed, this is the stellar surface density distribution of the redshift 1 sample. Okay, if you go back, let me just go back here. This was the imagery. And so now we go forward. And this is the stellar surface density distribution. And you clearly see fairly regular structures at all masses. And also, since all these All these images are on the same stellar mass scale, the development of very substantial bulges at the higher masses. Here's redshift 2, which before looked fairly irregular. Still looks a little more irregular, but also the same pattern. You can see the buildup of these red central concentrations, which are bulge to total ratios of 0.2 to 0.5. So these are very substantial bulges. You can also see in both of the images I showed you relatively few major mergers ongoing in terms of the stellar distribution. So that's the stellar distribution. The next one is the kinematics. And so here this is redshift 1. And so what you're seeing here in red and blue is the redshifted and blue shifted H alpha data extracted from the integral field unit. Of course, the resolution here is about half arc second, so it's not as good as that of the HST. Now let's just recall how you interpret these kinds of data. If you had an ideal exponentially shaped rotating disk, then in terms of the velocity first moment, which is the middle of these diagrams, you would see what is called a spider diagram, where you can see a regular change of velocity along the major axis. And if this is really a normal, regular exponential disk, then this kinematic axis, or called line of nodes, should of course coincide with the morphological major axis. So clearly that's already two constraints you want to see on these data. One, a regular change in velocity, if you can, the spider diagram, and change in velocity should happen along the major axis of the morphology. Then in terms of the second moment, which is the velocity dispersion, due to the beam smearing of the rotation, you always should get a peak of the velocity dispersion at the center of the distribution. And if everything is regular and you have a bulge, well then, of course, that peak of velocity dispersion should occur at the center of the stellar surface density distribution. So that's another criterion. So, with other words, in describing now in a statistical sense the properties of these velocity curves here, we would basically go ahead and for every one of them establish these criteria. Is there a regular velocity gradient? And if so, is that line of nodes along the morphological line of nodes? Is there a velocity dispersion peak in the center? And is it coinciding with the surface density distribution? So here's the redshift 1 distribution. And you can see that most of these diagrams are fairly regular. I want to emphasize, actually, it's also still reasonably regular down here in the below the main sequence for those objects where we have that. Here's redshift 2, and pretty much the same picture. Okay? So for us, that's not surprising, but I hope for you, it shows that you're now with a much larger sample of about 350 galaxies so far, where we can do this. We can see, indeed, this occurrence of what looks like regular velocity patterns. And the statement we're making in the paper by Emily Wisniewski, summarizing the first 1.5 years, is that at sufficient resolution, at least 70% and perhaps as much as 80% of the massive star-forming galaxies in these redshift slices are dominated by large-scale orbital motions. Now, mind you that a single velocity gradient, and perhaps even along the major axis of morphology, still might be, harboring an interacting galaxy system, which is somehow not obvious in the stellar surface density map. So I would say, in any individual system, you might still be have to be cautious, but statistically, I would say it's pretty clear that this is mainly rotation, and that major mergers are fairly rare. In terms of minor mergers, we can say still very little. I think for that you need adaptive optics quality data sets. We do have that, of course, for a subset. And indeed, we do see some minor mergers, maybe 10, 15% or so. But then, indeed, the large-scale velocity maps do not react to this very strongly, as you wouldn't expect so. So with that in hand, we can now analyze the broader statistical properties of this set of rotating galaxies. I remind you, of course, there's a large component of dispersion turbulence, which I've discussed here in the past. I won't dwell on this today. But now basically go from the measurements of disk sizes, masses, stellar masses and gas masses inferred from the star formation rates through scaling relationships, the velocities, velocity patterns which you've seen here, and the velocity dispersions to a variety of derived physical properties. And I start with the lambda parameters of the halo. So this is work Andy Burkert has led, where basically we fit to every galaxy with Monte Carlo fitting an NFW halo on an exponential disk, and then derive then from that fitting the best fitting halo parameters. So we get from that the ratio of the stellar or baryonic mass to the dark matter or halo mass, and we also get the lambda parameter. So here is a simple diagram of the 360 best galaxies, for which we can say these are, to our best knowledge, rotating systems. And from that we can derive the mean baryonically inferred halo lambda parameter, and that's 0.035. So that's very close to dark matter, what you would expect from dark matter. Okay? So to first order, I think what this data does show is indeed, as has been assumed in the theoretical work in the field by most people, is that on average, what comes into the disk in terms of baryons has sort of the same angular momentum properties as that of the dark matter. Now, as a number of people have pointed out, in particular Danovich and Avishai's group, is how that comes about, maybe a much more complicated story. So you may start off at the halo scale with actually too much angular momentum in the baryons, and then you dissipate some of that, and then in the end you end up with something. But at least here we know the end product on average, indeed, is about that of the halo. Now there's, technical discussion one should go through, and which we are going through in our paper, how reliable this work is and the assumptions you make here. We have also used different techniques to establish basically that indeed, for instance, the log normal distribution, which you see here, which is exactly that what is expected of dark matter with the same dispersion of about 0.2 in the log, is sort of reliable, and I think it is. So the next thing is you can turn this a little around, and instead of deriving through this fitting technique a halo angular momentum parameter, you can also go more empirically and basically calculate the specific angular momentum of the disk, J disk. Okay, just the angular momentum divided by the stellar mass or disk mass. And you assume a halo angular momentum parameter to be the same for all objects. Now that's not the case, of course, because we have a log normal distribution. But to simplify this, let's make that assumption. Then you can actually derive empirically the ratio of the disk-specific angular momentum to the dark matter angular momentum. So this ratio, of course, as we know, is exactly what we're looking for. Is there dissipation? Okay? So in this plot here, where we're plotting now JD over J dark matter after, in fact, applying some recipes having to do with the fraction of the stars in the baryonic disk due to Dutton et al. But you could also use abundance matching results, Moster or Berozzi. And then you get in blue here the majority of the high redshift disks. And in red, you see the local late-type disk galaxies from the sample of Fawn and Romanovsky. And you see 0 on this scale, of course, again, means that on average, the baryonic material has the same angular momentum as that of the dark matter, both at low and at high redshift. So that's for most of the galaxies. But now if I select out of our sample those galaxies which have a very high surface density, or Guillermo would like to say, let's pick the parameter m star over r to the 3/2 and pick objects which have above in the log of 10.3. Same thing. Then all of a sudden, a new group of galaxies at high redshift appears, which is labeled here in block green. Apologize for the selection of colors here. And see that group of galaxies samples, these dense galaxies, sample the higher mass end, and they have obviously a disk over dark matter ratio below 1, significantly below 1. So that confirms and strengthens the interpretation which Guillermo and collaborators had, that this group of objects has suffered some angular momentum loss. Now it's a little tricky, of course, if you discuss this, to distinguish that conclusion from the one that, they all had initially already a low angular momentum parameter. The argument here goes, basically, it only appears, this group of objects only appears on the right side. You want me to finish? Is that?
No, 5 minutes, but allow a little time.
Woo! Okay, so that may in fact strengthens the conclusion on compaction. In terms of the baryonic mass fractions, I should say what we are seeing in the blue objects, that's the ratio of stellar to halo mass, is very good, in good agreement with the overall, with the abundance matching results of the different groups, which are in these different curves, the Barozzi, Wechsler et al. Curves, but also the Moster et al. Curves. And, however, since gas is at least half the mass at high redshifts, the effective baryon fractions are not 15% or 10%, but they're 30%. Okay, so that needs to be kept in mind, that the stellar fractions have to be corrected upwards. On the disk scale, we find that about 75% of the matter on the disk scale is baryonic. So these are highly baryon-dominated systems, where in the local universe the numbers would, in this mass range, would be somewhat lower. And then finally, a very recent result is we have been starting to stack rotation curves. So we want to go onto the halo scale and basically map out the rotation curves, very much what was done in the local universe in the 70s and 80s. And the surprising result, which you see there in the central U graph, is we're seeing that the rotation curves in individual galaxies, but also in stacks, is dropping. One explanation which we're exploring here is that in addition to the strong baryon domination in the centers which I just mentioned, these objects, because they have so much dispersion, are dispersion truncated. Basically, as you go out in radius, if the dispersion stays constant, which we cannot test because we cannot make that measurement, if you assume that, then the pressure term will dominate at higher radii, and thereby leading to a fact that basically there's a truncation of the rotating disk.
What redshifts are these?
The same sample. So it's all in there. If I slice this into the different redshifts, we don't see any differences. Okay, let me, since our chair is threatening, let me really tell you about the progress on the outflows, because it seems to me that's really a very nice progress. So I showed you some first results with 50 objects 2 years ago. Here's now 450 galaxies. Red is redshift 1, blue is redshift 2 as a function of stellar mass. So we get profiles, and we can stack the profiles after removing the rotation, actually, in order to search for broad components. So when we go to the lowest slice here in mass, what you see is a blue curve and a gray curve. The blue curve is the nuclear region. The gray curve is the outer disk region. And you see H alpha there, you see nitrogen 2. You see there's not much difference. There's also not a broad component whatsoever. So that's the low mass end. Now we go to the next slides. Now you're beginning to see, if you squint sharply, well, gray and blue is still the same, but you see a little bit here which is not going to zero. That is actually evidence for an outflowing component, although of moderate width, which is present in the outer disk as well as the nucleus, so that we would call stellar feedback. Go to the next higher slice, still the same. Gray and blue coincide, but you see this outflowing component is more prominent. And then above 10.9, so about the Schechter mass, something really interesting happens. All of a sudden, the gray and the blue do not agree anymore, which just means there's something special in the nucleus. And this nuclear component, after removing, so we have removed here the star-forming gas, okay, is very broad. In fact, there is a tendency in this plot here, apologize for the quality, that the galaxies which are below the main sequence, which are the blue ones. This is a stack of the blue below main sequence galaxies, have broader and fractionally much stronger outflows from the nucleus than the above main sequence galaxies. That's the red one. So they are very prevalent. In terms of incidence, okay, well, I guess I should say, for a small number, we have spatially resolved information. That spatially resolved information tells us that, in fact, whilst this component is in the nuclei, it is actually spatially resolved on scales of a few kiloparsecs. And so it's not a broadline region. It also shows up very prominently in Nigen 2, as you see here. In fact, it peaks on Nigen 2 in the stacks, but it's also there on the sulfur 2. Okay, and so then it's resolved, therefore it must be an outflow. So that's the last slide, Joel. So here's the incidence. So this is now based on 400 galaxies. In each of these points, you have about 80 galaxies in stacks. And so this is the incidence of this broad component. And you see it rises very sharply at high masses. And it does appear to be more common than AGNs in the sense of X-ray, mostly X-ray detected AGNs. You can discuss this at length, what that means. I think it's just a question of the depth of these typical AGN samples. For instance, Cosmos is not very deep, of course. And so what I think you're seeing is that about 2/3 or more of all high mass objects selected only on their stellar mass star formation rate properties have these nuclear outflows. They are probably powered by an active, by a black hole which is accreting, but it only makes it into the so-called AGN sample of somebody above a certain limit. So actually, the high duty cycle tells us, together with the high velocities and also the high mass outflow rates, that this is indeed a very important component which may have something to do with driving gas out at high mass. I hesitate to say that this is the proof, so to speak, for this AGN feedback in the QSO mode, but I think it's certainly hinting in that direction. Thank you.
Thank you. Could Reinhard Genzel please set up? So while the next speaker is setting up, Sandy?
So, listening to your talk, I would take away the general message that the kinematic properties at Z of 1 are very similar to the kinematic properties of Z of 2. And so I'm very interested in changes that you might be seeing between those two redshifts. And let me just ask you to qualify a little bit more carefully your statement that, what was it, I think 70% of massive star-forming galaxies are dominated by large-scale orbital motions, but the sample is 0.8 to 2.6. Let me ask you, if you can, to break that into a high redshift and low redshift sample and comment separately.
Right, so of course it's been done in the paper by Emily Wisniewski, which is out. You will find that, formally speaking, the redshift 2 numbers are a little lower. Okay. If you look at the velocity profiles, which I did show, they're looking a little less nice, okay? But statistically, I don't think you can make up at this point that there's a difference. But
Is there any difference with mass?
No. Now, mind you, we do not sample below 10 to the 10, okay? So I would say we know already from symphony work prior to this, that as you go to less than 10 to the 10, you encounter an increasing fraction of what we called at that time dispersion-dominated galaxies. Although, when you go at it with high resolution and high quality adaptive optics data, you often find that what you called a dispersion-dominated actually then does show velocity gradients when you have the data. But still, I would say, indeed, mind you that this only goes from 10 to the 10 above, and it may very well be, possibly, that below 10 to the 10, some of the story changes. We don't know that yet.
I think we better move on because we have a very crowded schedule. Obviously, Reinhard has given us a lot to think about. So the next talk is by Reinhard Genzel.
And you can couple it with adaptive optics and laser stars, so that you get about 1 to 2 kiloparsec resolution. And so that's been a very successful project. Over a decade, we were able to assemble about 110 objects, which of course is a very small number. So the big progress which is happening right now, both on the KEK with MOSFire and, as you will see, on the VLT with KMOS, is to now go into an era where we can do many more objects by multiplexing. Now, with KMOS, we have a situation where, due to the work, and so today I decided to pick 3 topics of our new work with mostly KMOS, as you will see in a second what that is. And that is a study of the angular momenta, Baryon fractions, already pushing out into the halo, and then also the outflow story, which is further emerging. Now this is work which involves a large number of people, in particular Natasha Förster-Schreiber, Andy Burkhardt, who is sitting in the back, Linda Tacconi, also sitting in the back, Emily Wisniewski and Stein Witz. And
the talks are all being video recorded, and that's why you have to use the microphone, because otherwise the video doesn't pick up the audio.
Very good. Okay, so good morning. I apologize for this wonderful bar down here. You don't know what it is due to. It must be a European feature. So I've regularly used in the past this occasion here to show some of our new work, and we'll do that again. Linda Tacconi on Thursday and I here, and a whole set of characters from mainly the KMOS 3D team in Munich. Okay. So the work we've been doing over the years is concentrated mainly on integral field spectroscopy in the near-infrared on the VLT, and until recently we've been using the Symphony spectrograph, which is a single IFU unit. Hopefully we can get the picture too.
Just working. It was.